Good afternoon, OffensiveCon. It's good to be here. Good to see so many people here. Yeah, I'm talking about user mode code integrity, which is a technology Microsoft added originally in Windows 8 and was deployed on Windows RT, which was the ARM-based Surface laptops. And what it effectively is sort of an application whitelisting solution. It allows you to restrict what signed applications are allowed to run on your system. If this application is unsigned or it's not signed by a specific certificate, in the Windows RT case, specific certificates from Microsoft, it would not actually allow you to run that executable. And the idea being malware can't get on your system and all that good stuff. Now, actually configuring user mode code integrity on Windows 8 was quite difficult. You needed to install secure boot policies. And while you could turn it on for x86, it was not really documented or supported. Now, the big change is that very recently, Microsoft introduced Windows 10s, which was originally a SKU. Now, apparently, it's just a mode. I think that's probably splitting hairs a little bit. But effectively, it's a new consumer version of Windows RT, and it's streamlined for security and superior performance, apparently. I think this is a bit of PR spin, of course. But it's sort of like Microsoft's response to Chrome OS and restricting everything to browser or only store applications. You can download stuff off the store because it's kind of signed by Microsoft. So let's have a very quick introduction to the architecture and how UMCI actually works under the hood. Now, there's actually two components to UMCI. The first one is actually the enforcement of executables and DLL loading. So when you actually load an executable or when you actually load a DLL, you actually ask the kernel, can you create me something called an image section, and then can you parse that PE file and map it into memory? And what the kernel can do at this point is request the services of the library in the kernel mode, the ci.dll, the code integrity DLL, and say, could you verify that PE file, the signature of that PE file, against some sort of system integrity policy? And the system integrity policy used to be part of Secure Boot, but is actually now a file on disk. And you will also heard this referred to as using device guard, a device guard policy. And this can be provided by the user, but in terms of Windows 10s, it's provided by Microsoft. And this effectively enforces signature verification on executables and DLLs. So you can't load an untrusted binary. But what about all those applications which run in user mode on a standard Windows system which could act as confused deputies, could load arbitrary script code and give you, for all intents and purposes, arbitrary code execution anyway? To do a bit of mitigation against that, Microsoft also has something called the Windows Lockdown Policy. And the Windows Lockdown Policy is implemented in this WLDP DLL. And it allows what could be referred to as enlightened script engines. So most of the script engines on Windows, such as PowerShell and Windows Scripting Host, are all considered to be enlightened. They know about UMCI, and if UMCI is on, they will actually enforce additional restrictions on that scripting content, whether it be, in PowerShell's case, turning on something called constrained language mode, or in the script host case in JScript, it will actually restrict what COM objects you can access. So actually, if you want to test Windows 10s, you could buy a laptop. This is actually, I'm using a Surface laptop which came with Windows 10s, and it was obviously, after I'd done some testing on it, it's quickly upgraded to Windows 10 Pro. But you can install versions of Windows 10s from an ISO. I'd highly recommend if you're going to do that using Hyper-V, because then you don't have to install non-Microsoft virtualization guest editions, and so everything works and your screen resolution all works and all that sort of stuff. So this is specifically version 1703 of Windows 10s. So this was the one I researched originally. This is also RS2, and there's also a build number as well. And so all the bugs I'm going to present in this are all based on that research. Now, the actual policy file itself is inside the Windows boot EFI folder. There's actually also on the boot partition as well. And right at the bottom is this Win SI policy, P7B, which is a PKS7 container, which is a signed container containing a binary blob, which is our system integrity policy. Now, that system integrity policy is kind of hard to read. I can read some binary, like hex dumps, but there's a limit to how much I'm willing to go. Matt Graeber actually released a tool to convert the binary blob back into an XML file. And so this is actually the policy of the XML file. And some may argue whether XML is more readable than binary data, but But the XML file contains a number of components. For example, it has a list of rules. So in this particular case, you can actually turn device guard on without UMCI, so it just enforces kernel mode code integrity. In this particular case, it definitely has UMCI turned on. You have various signer policies, so in order to have a file loaded, it must not only be signed by a particular certificate, which is most of the time Microsoft certificates, it also must have a special enhanced key usage added to the leaf certificate, which says why it was signed. And for example, there is the Windows System Component Verification, and this EKU indicates this file is a signed Windows binary. So not just a Microsoft binary, it was signed for the purposes of distributing with Windows. And then possibly of more immediate interest from actually finding interesting bugs is the list of banned executables. So this is based on file name, but it's not actually the file name of the file on disk. Instead, it's the original file name in the resource section of the PE file. And because this resource section is part of the signed content of the PE file, you can't modify it without invalidating the signature. So it allows the device guard policy to ban specific types of files. So for example, they ban cmd.exe, they ban wscripting host, Windows scripting host, so C script and wscript. They ban PowerShell, which is unfortunate because when I did similar research on Windows RT, I abused PowerShell to get arbitrary code execution. They also ban simple tools like tools to edit the registry. So in theory, you can't modify the registry trivially without actually getting arbitrary code execution in the first place. And obviously, if I just sort of demonstrate that, if I try and run reg.exe, which should be a banned executable, we get a big blue dialog and it says, sorry, that is not allowed to run, and it's there for your own protection, so just please ignore me. So as with most of my research, I'll always try and come up with some sort of goals, because you kind of want to measure your sort of whether you've succeeded in your research. And what I kind of wanted to build was something which you could kind of just drop and run on the system, only using built-in applications, because for all the PR puff about Windows 10s being super secure, it was pointed out like about 4 or 5 days later that if you install Office still supports macros, whoops, well, you can get arbitrary code execution. But I wanted to obviously not use Office because that had already been done. I'm not one for memory corruption, as probably people who've seen my presentations before will know. And I wanted sort of arbitrary code execution, which gave me the ability to not just pop calc, but pop notepad as well, maybe, or something else. But like complete control over the system without requiring admin privileges. So those are my ultimate goals. So I thought, okay, let's start with bypassing the user mode component, because that's what I did before. I used PowerShell to effectively circumvent WLDP. Now, most of the obvious scripting engines have been ruled out. WScript and PowerShell are all gone. But one thing which you could do is abuse the fact that the MS-HTML HTML renderer runs something called local machine zone. And if you run a file from the local hard drive, it runs in this local machine zone, which allows you to run effectively arbitrary script code, which can instantiate arbitrary COM objects and manipulate the system and do nasty things. Now, you can run it in Internet Explorer, but like the file format .html, if you double-click that in a dropped file, it's going to load in Edge, and that doesn't help us. It has to run inside Internet Explorer. However, another useful file format, the compressed HTML file format, which is part of the HTML help engine, is just something you can just double-click. It would automatically run. And this also runs in local machine zone. Now, there is a slight caveat from a drop-and-run perspective. You do get this dialog. If it's got marketer web, which is because it's downloaded from the internet, the user would have to uncheck this tick box and click open. Otherwise, it won't actually run in local machine zone. But maybe you could convince the user to do that. So I knocked together a really, really simple script, and I know I said I wanted arbitrary code execution, but baby steps here. I'm just going to pop calc. If I can pop calc, I can probably pop something else, right? And I put that into a compressed HTML file, double-clicked it, and I get this error. I get basically an error saying, I cannot create the wscript.shell COM object. And that's the problem. If I can't create a COM object, well, JScript is virtually useless if you can't create COM objects, because that's the only way you can interact with the rest of the system. And it turns out I was just late to the party. Now, Odvar and Matt Nelson had already discovered that for some reason MS-HTML's renderer in local machine zone was not enforcing the Windows lockdown policy. And it turns out Microsoft had fixed it in 1703, the build I was using, but not actually released details that they'd fixed it. It was only a couple of months later that Microsoft actually released an update on Patch Tuesday which fixed the down-level platforms, and then everyone knew it was actually fixed. So that's kind of disappointing at that point, but you can't just stop there, of course. So I thought, okay, how is it actually being enforced? And I stuck MS-HTML into IDA and had a look, and what you'll find is that it was checking a particular flag when it was instantiating a COM object. It was being passed the class ID, and the class ID is a GUID, which refers to a specific type of COM object. And it was passing it into this WLDP is class in approved list function, which is part of WLDP. So the question is, what is that function doing? All that function does is compare that class ID to a list of 8 hard-coded class IDs. For MS-HTML, you've only got 8. If you're in Windows scripting host, there's a further 58 that it could be. But it turns out, of those 8, only 3 of those classes are actually registered on the system. And while file system object's kind of interesting, you can read and write arbitrary files, it doesn't give you arbitrary code execution. And yes, there's been bugs in the VB script regular expression COM object before, but as I said, I didn't want to use memory corruptions. But the interesting thing is, what if I registered a COM object which happened to be using one of these allowed class IDs, but actually created a completely separate COM object under the hood? Would that work? Would that bypass the restrictions? So it then becomes a question of how does MS-HTML and JavaScript create COM objects? Now you would normally call new ActiveX object passing in this string, wscript.shell. wscript.shell is something called a programmatic ID, and is basically just a moniker for referring to a particular COM object. So underneath the hood, JavaScript calls class ID from prog-ID, which is a system API, and that looks up that string and returns you a class ID. That class ID is then passed to isClassAllowed, which then passes it to co-create instance, assuming that isAllowed is actually set to true. So there's probably some sort of timer check, timer use issue here in that obviously when we're checking the class isAllowed and then creating the class with co-create instance, there's a lot of things which could go wrong in between those two steps. And so if I could get the class ID to return a valid allowed class ID, but when passed to co-create instance, actually created a completely different class COM object, then I would win. And one trick to doing that is something called the treataz key. And the treataz key is kind of like a symbolic link for COM objects. You can link one class ID to a completely different class ID. So this sounds perfect. I can just register. Interestingly, I can register it in current user, so I do not need admin privileges. I can register a allowed class ID, but point it at an unallowed class ID, and hopefully, when it loads up, it will allow me to instantiate that COM object, but when co-create instance is called, it would actually create the object I really want, not the one I'm pretending to be using. But then we hit a problem. We're on a standard Windows 10 system. How on earth do we get anything in the registry? Because as I said, most of the registry editors are banned. reg.exe is banned. regedit32.exe is banned. If you run them, it just says you're not allowed to do that. So I looked in system32, and as you can see, reg.exe, regedit32.exe, all banned. But what about regini.exe, the exact next one in that list of files? Turns out it's not banned. What the hell is regini.exe? Well, regini.exe takes an ini file format which installs arbitrary registry keys for you. So obviously I can install my registry keys from that. But when I tried it, it doesn't work. And the reason it doesn't work is class ID from prog-ID is cleverer than me, obviously. What it actually does is when it's looking up that string, it's actually following all the links and it follows all the treataz keys and ends up returning you the class ID which is banned but the one you wanted to create. So by the time it calls isClassAllowed, it still says you're banned because you're not allowed to do that. And so we obviously get the same error. Fortunately, we're in HTML, and HTML has the object tag. And the object tag takes a class ID attribute, which just takes a GUID, And the sort of corresponding conversion function, class ID from string, just converts the GUID to a GUID string to a GUID. It doesn't verify that that GUID exists or anything like that. So at that point, our class ID can be in the allowed list, but when co-create instance is called, we obviously create an object we didn't expect. But again, great. This is only going to allow us to pop calc. Have we got something better? Well, you can use my .NET to JavaScript tool. This allows you to bootstrap arbitrary .NET code from memory, which circumvents the code integrity policy from JavaScript, and you get arbitrary code execution that way. So let's quickly demo that. So I've got my list of keys. So this is just to set up .NET to JavaScript, redirect all the COM objects. I can just run a link, and obviously you could use the file system object to drop this link into the user's startup folder. So just running it could drop these link files and install the registry keys for you. So I'll just double click that, and you see nothing because the window pops up and then disappears. But now if I run this CHM file, we should get a copy of PowerShell running. So I reported that to Microsoft because I thought I probably should do. And Microsoft fixed it, although they didn't necessarily proofread the report, because obviously it's nothing to do with PowerShell. But you can have a look at more detail of that if you like. So that's great and all. I can now run arbitrary .NET code. Awesome. But not everything is written in .NET. It would be kind of nice if I could run arbitrary executables, like completely anything I liked. So like Process Explorer, for example. Can I do that? Well, when I was poking around, I queried for like the mapped images. So these images should all be signed. They should all be verified by the code integrity policy in the kernel. And I noticed that there was a lot of native image executables loaded into my process as image files. Now, if you don't know what these are files, DLLs generated by the NGen process. And NGen is an ahead-of-time compiler for .NET. And it allows you to obviously increase performance because it pre-converts the CIL assemblies into a native binary. But the funny thing about this is NGen usually runs on target, so they can't be signed by Microsoft. They can't have been pre-signed and deployed because they would be generated on the target system itself. So that's kind of interesting. So I had a quick look, and yes, that DLL file is not signed according to the standard rules of signing. It has no embedded signature, it's not part of a catalog, and if you copy that file somewhere else, it no longer works as a mappable image. And that kind of implies that it's not some sort of hash stored in memory, it's something to do with the file itself. And what it actually turned out to be is related to a special extended attribute. So most people don't necessarily realize this, that NTFS supports the ability to have name value pairs added to an arbitrary file, and this is extended attributes. And under the hood, the name of this particular extended attribute was $kernel.purge.esb cache. And if I remove that, or manipulated that in some way, then the file would no longer be mapped as an image section. So I thought, okay, what does that actually do? Well, if you actually look on MSDN, there's actually an entire article about this and how it's basically there to speed up the verification of sort of pre-cache image verification, because actually verifying an image can be quite an expensive operation. So by pre-validating that image and storing it as a cache, well, we can then just go, is that cache there? If it is, awesome, we already assume it's signed. But the trouble with this is, what if a user application tries to spoof this information? Well, fortunately, the designers thought of this problem and tackled it in two ways. Firstly, the $kernel prefix of the name indicates that this extended attribute can only be set from kernel mode. And more than that, it can only be set from kernel mode using a special function, a special minor request code as part of the ERP. And if you don't do that, you just will not let you set that extended attribute. So that stops a user mode just adding an arbitrary entry to a file. But what about if I just modify an existing cache signed file? Well, at that point, the NTFS driver notices that through something called the USN change journal, and it sees that you've tried to overwrite the file or truncate the file or modify it in some way, and then automatically deletes it for you. So as long as that thing exists and you trust all the other operations are working correctly, then if anyone tries to modify that file or spoof it, then it will automatically be deleted and your cached image signature will go away. Okay. But of course, there must be a way of doing this from user mode, and when Microsoft added a system call into Windows 8, the NT set cache signing level system call, really complicated naming there, and it takes some flags which indicates a couple of different operating modes. It has mode 0, which is the one used by NGen, which allows you to sign unsigned files by effectively applying a signature from an existing signed file. But in order to use that mode, you need to be inside something called a protected process light process, which is a special isolated process mechanism, which you need to be signed by Microsoft to get in theory. So if you need to be signed by Microsoft, well, you've probably already got code running on the system, so you don't really need to do this. But what I found interesting, there was a second mode, this mode 4, which allows you to cache the signature of an existing signed file. And for this, no PPL was required. So I thought, okay, how does that actually work under the hood? And what actually happens is, first, the user mode has to open the file it wants to apply the cache signature to. And obviously in mode 4, this also needs to be the one which is also already signed. Now that signature can be embedded. It can be an embedded authenticated signature, or it could also be something called catalog signed. And in catalog signed, what you have is you do a cryptographic hash of that file, and then you go and search a load of catalog files which are installed as part of the system, and in these catalog files is potentially your hash, and then that entire catalog file is then signed. And the majority of Windows binaries are catalog signed as opposed to embedded signed. So we call this set cache signing level requesting mode 4. We then, obviously the kernel has to then hash that target file and produce a SHA-1 or a SHA-256 hash of it. It then has to find the catalog which corresponds to that hash and verify it. And then finally, if the verification is successful, it makes sure that there's no pending writes to the file. It flushes this USN change journal and then writes the extended attribute. And then from then on, you cannot no longer modify the file. But what I found interesting was the fact that because we not passed the file path, we just passed the handle, throughout this entire process, user mode has access to this target file. However, only the first couple of steps require that file not to be modified. Up until the point where the file is hashed, anytime after that, up until the point it tries to write the kernel attribute and flush the change journal, in theory, we can actually modify the file. So is there a window of opportunity in this little space that we can exploit and effectively sort of modify the file and get it to cache sign effectively a file it didn't expect? So let's hope this demo works. So I've got Process Explorer. I'd really like to run Process Explorer. And Process Explorer is a Microsoft signed binary, but it's not signed with the correct EKUs, which allow you to run it on Windows 10s. So I can run this. So if I copy processexplorer.exe and I want to create procxworking.exe, oops. Okay, so it seems to do some funky stuff. And now if I run but actually, just to double check, if I do fc.exe, which is a file comparing the two files, there's apparently no difference between the two. But if I run Process Explorer working, we get a copy of Process Explorer running. And this is a completely arbitrary binary, and you can apply it to DLLs, you can apply it to XEs, it doesn't really matter. Now, okay, again, I kind of thought I probably should report this to Microsoft, and so they fixed it. So in terms of goals, did I meet my goals? I think I met pretty much everything. Other than the drop and run, there was far too many dialog boxes I had to click through and potentially get the user to uncheck a tick box and all that sort of stuff. But in theory, you could get, with a bit of social engineering, get them to run a binary which would then compromise the system for you. Or use it as a jailbreak. Like you could get someone to say, if you want to jailbreak your Windows 10s device, you could just double click this and do some fun stuff. So it's all fixed, and Windows 10s in RS3, which is build 1709, is obviously completely secure. So let's demo some stuff on Windows 10s on 1709. Let's try. So obviously the wonders of trying to, okay. Right. So, yeah, okay, log in. So this is 1709 I updated on Tuesday, so it's completely up-to-date version of 1709. And there was a few changes. For example, if I run regini.exe, it goes no, and HH, which is the HTML help, goes no. So they banned this, so clearly it's going to be super secure. And obviously PowerShell is still banned, but there does happen to be a PowerShell icon on my desktop. I wonder what happens if I double-click that. We get a copy of PowerShell, right? Okay, but again, they fixed my arbitrary code execution bug. And I hate Edge, obviously, because I must do so. I really want to run Firefox, right? But Firefox is not allowed. So I'll just run this little script. Goes off and does some stuff. And then if I double-click Firefox now, if you give it a second. So it's fixed, right? So if you want some references, there's some references. There's things like my .NET JavaScript tool, a MacGraber's tool to convert the binary policy file. And I'm not going to obviously explain how I did that on 1709, but all that information is out in public. It's not fixed, but you can find out what it is if you go looking. So thank you very much for listening to me, and I hope you have a good rest of the day, but thank you for listening. Thank you.